Well, thank you everyone for coming tonight. As Paul said, I'm going to look at the Phanerozoic history of the Pilbara region from about 300 million years ago. And those of you who know me well will know that most of my career has been spent in the Archean. So this is a bit of an excursion for me. But I believe there are serious implications for the incredible iron mineralization that we see in the Hamersley province. And this material has been recently published in the Australian Journal of Earth Sciences, so I'd just like to acknowledge my co-authors, John Hronsky and Matt Crowe. So the Hamersley province, most of you in this room will be aware of where that is and that it's a world-class iron province. So the image on the left shows a geological map. The Hamersley province is situated on the southern margin of the Pilbara Craton. It's shown there, the Hamersley group is shown in that brick red colour. And it's a 2.5 kilometre thick sequence of sedimentary rocks, Archean to Proterozoic sedimentary rocks and volcanic rocks. But of main significance to us tonight is the fact that it hosts the Marramamba and the Brockman iron formations. Now, the image on the right there shows the outcrop of the Marramamba and Brockman in yellow and pale blue. You can see there's a lot of BIF outcropping in the Hamersley province. But more importantly, there's also an awful lot of iron mineralization. So this is data from the GSWA. Those are iron occurrences, they're not all mines, by the way. In pink are the hypogene martite, microplaty, occurrences. That's things like Tom Price and Paraburdoo and Whaleback. These are Paleoproterozoic, and I'm not going to discuss them any further. Well, they're Proterozoic, shall I say, at least. I'm not going to discuss them further tonight. What I do want to look at are the two types of deposits, the MG or martite-goethite ores, the supergene, and the channel iron deposits, or CIDs. These are two styles of mineralization, very much younger, they're Phanerozoic, which are rarely found in economic concentrations anywhere else in the world. And so why is it that the Hamersley province is so incredibly richly endowed? And as we go forward, the mining industry in WA is going to be increasingly reliant on the MG style of mineralization for its resource base. We've pretty much mined out most of the really high-grade microplaty hematite mineralization since the 70s. So the mustard yellow and the blue dots there, those are the martite-goethite style deposits in the Marramamba and Brockman iron formations respectively. And the orange stars there are the CID or channel iron deposits. You can just see in pale orange is the distribution of the Robe River pisolite, which is the host formation for those fluviatile pisolytic ores. Just a quick outline, so I'm going to quickly introduce you to or give you an overview of the two different mineralization styles, the martite-goethite or MG and channel iron or CID deposit styles. Then I want to do a rapid geodynamic overview of the last 300 million years, so from the late Carboniferous, early Permian glaciation through a burial and subsequent denudation of the West Australian Craton, through uplift and incision of a series of major paleo valleys. Then I want to look at what the climate's been doing over that same period, or at least over the last 100 million years. There have been intense periods of lateritic weathering, capped off with a trend to aridity from the late Miocene. And then finally, I want to come to the conclusion, what is it? What is the key to this incredible iron endowment? So first of all, the martite-goethite mineralization. Key characteristics, well, these deposits are Eocene to Oligocene in age, broadly speaking. We believe the ore fluids were acidic and reducing, and this is probably telling us that there was abundant organic material near surface. These are supergene deposits, so essentially the ore fluid is modified rainwater. The ore fluids strip iron from the banded iron formation in the vadose zone, and this probably suggests that this requires uplift to replenish the source region if you're going to have a mineral system that exists for some time and produces a decent sized deposit. If in a supergene environment, you generally need uplift so that you can replenish that source region near surface. Petrography tells us that this is there's three stages of petrogenesis that can be viewed under the microscope. It tells us this is an evolving system and possibly quite a long-lived one. And finally, there's a distinct lateritic weathering overprint. So it's important to realize this is not just ordinary lateritic weathering. This is a completely distinct style of mineralization that we can see has been overprinted by lateritic weathering. And the cartoon on the right just illustrates that in a little sort of 3D model there. So we have rainfall leaching through organic matter on the surface, picking up humic acids, reducing the pH, sorry. I shouldn't have had that beer, should I? Then it percolates down a long bedding through the vadose zone, which is illustrated there in blue, picking up iron, so leaching iron from the BIF protoore, leaving behind a residual iron-leached BIF. Very silicious material left behind. Then it hits the water table. The ambient water table, groundwater is likely to be slightly alkaline, and it's probably the interaction between the acidity in the ore fluid and this ambient groundwater that triggers the mineralization. So we have the MG ore formation, that's the zone shown in pink there. At the down dip, sort of outflow end of the system, often there is relict quartz left, so the mineralization hasn't gone to completion. We have this sort of zone of silicious mineralization shown in turquoise there. So that and the images on the bottom right are an outcrop view of the beautiful martite-goethite mineralization. The chocolate brown is the martite layers. Martite just means hematite replacing magnetite pseudomorphically. And the mustard layers are goethitized gangue phases, things like silicates, carbonates, and quartz. And a photomicrograph on the right of the same thing. Moving on quickly now to the channel iron deposits. The key characteristics here are that the channel incision, these are fluviatile deposits, or at least the host rock is a fluviatile deposit. Channel incision occurred starting probably in the late Eocene. Clearly, you can see from the map view in the top right there, clearly these sediments accumulated in meandering rivers, suggesting that the terrain was fairly flat at the time. The rivers have been incised into Wheelie Wally Formation, which is a mixture of dolerite and BIF, pretty iron-rich to start with, and this is probably the source of the pisolites that make up a large proportion of the sedimentary input to these bodies. It's also probably the source of the iron, the cementing iron as well. Channel infill or aggradation took place in the Oligocene to Miocene. So the pisolitic cores are hematitic, but despite the fact that they're probably derived from the surrounding BIF-rich Wheelie Wally Formation, there's no trace of finely laminated bedding preserved in these hematitic clasts. So it does suggest that they're perhaps derived from a deeply weathered terrain where you had a ferruginous jury crust at surface at the time. Also, the pisolite cores are dated to between 65 and 60 million years old, so they're significantly older than the event in which the formation of the sedimentary sequence. And also, there are fossilized wood fragments that core some of the pisolites, and there's a paper by Dick Morris and Eric Ramanaidu that discusses these and speculates that they're likely to have been charcoal fragments, which does suggest that there was a distinct wet and dry season at the time that these pisolite cores were forming and being accumulated. Then we move on to the cementation of the pisolites. This happened in the Oligocene to Miocene as well over quite a period of time. Interestingly, the age of the goethitic cement does decrease with depth, and that's been interpreted to reflect a declining water table over time. And finally, the CID deposits now are preserved as mesas. So even though they were formed in a river valley, they now stand proud of the present land surface. So obviously there's been Pliocene to Quaternary uplift in the local area. And the two images on the bottom there, on the left is a hand specimen photograph, and on the right a photomicrograph. Okay, so let's start with our geodynamic journey at the time of the Permian-Carboniferous glaciation, so about 300 million years ago. The West Australian craton at that time, Australia was part of Gondwana, Antarctica was sitting pretty much where it sits today, so Australia attached to Antarctica was sitting at sort of subpolar latitudes. There were huge ice sheets that covered a large portion of the West Australian craton, shown here in the, sort of the white colour, basically. So ice sheets that were kilometres thick basically covered most of the West Australian craton. And essentially what this has done, the glaciation, there's precious little evidence of any older Phanerozoic material left on the West Australian craton. So the glaciation effectively reset the land surface. And we've called this surface the Precambrian surface because that's the age of the rocks that make it up. There is some evidence of glacial features that are preserved very close to the modern land surface around the periphery of the West Australian craton. So we have glacial geomorphology preserved in the northwest. We've got glaciated pavements preserved in the northeast. There's a beautiful photograph here taken from this GSWA publication by Maury. And around the Laverton area in the goldfields, there are these things called glacial tunnel valleys. So basically these are river systems and the sediments, associated sediments, that were deposited in stream systems developed underneath a melting ice cap. And those sediments are beautifully preserved and exposed in some of the gold pits around the Laverton area. Oh, sorry, I should say that. So basically, we're seeing glacial relicts on the margins of this craton. Now, you can interpret that in two ways. So one is to assume that, in fact, the West Australian craton has remained subaerial since the Permian. That's 300 million years. That's quite a big ask. The other is to suggest that the West Australian craton has been buried and then re-exhumed, and just coincidentally, some of these features are now preserved again at the current land surface or close to it. And new data does favour that second interpretation, so I'll go through that now. Essentially, between the Permian and the Triassic, there's some evidence that the craton was buried to considerable depths. So one line of evidence comes from the Collie Coalfields. So this is a Permian outlier of the Perth Basin. So you've got quite a thick sequence of sedimentary rocks, including coal measures preserved, about 1.5 or 1.4 kilometre thick section. They're preserved by downfaulting in grabens. However, the rank of the coal suggests that there's been at least 4 to 6.5 kilometres of rock removed since the Permian. That's an awful lot of rock, and it does suggest that the Perth Basin may once have onlapped considerably onto the West Australian craton. There are also provenance studies from Perth Basin sediments. Basically, the Perth Basin, again, contains a huge thickness of sediments dating from the Permian to the Cretaceous in age. You'd expect there to be quite a lot of Yilgarn-derived detritus, because, of course, of the Yilgarn block sits just inboard. This is the case in the Permian sequences, but by the time we get to the lower Triassic, there's no evidence of Yilgarn-derived zircons, for example, in those sedimentary sequences. This is at least consistent with the Yilgarn being covered by Lothrus sediments at that time. And there's a little image there at the bottom there from a paper by Weber et al. Showing a reconstruction of the Australia and, oops, wrong one. Australia and Antarctica in the Triassic, with a range of mountains that extended through what's now eastern Australia and Antarctica. And the major transport directions from that mountain range, well, at least from that portion of it in Antarctica, basically crossed across the West Australian craton. So bringing Mesoproterozoic sediments right across the West Australian craton into the Perth Basin and the Northwest Shelf. Moving on now to from the Jurassic to Jurassic period, and this is a period where there's some evidence that the craton was being denuded once again. So there's apatite fission date tract studies from the northern Yilgarn. They indicate that the basin, the craton was buried to considerable depths during the Permian, so temperatures up to 100 degrees Celsius, followed by slow continuous cooling into the Jurassic. And this is consistent with the removal of at least 2.5 kilometres of rock. There are a lot of uncertainties, but we're certainly talking about several kilometres of rock being removed during that period. There's other evidence from the Northwest Shelf, of course, where this is a period of major offshore sedimentation. There are a number of major deltaic complexes developed both in the lower to middle Jurassic here and again in the upper Jurassic. And interestingly, these ones are fed from, very much the point where today's modern river systems basically exit into the ocean at the Northwest Shelf. So by the time we get to the early Cretaceous, there is evidence that the West Australian craton was re-exhumed by this stage. So for example, we have early Cretaceous sediments like the Yarralula conglomerate here, which are preserved on the margins of the craton, and they're thought to correlate, these sediments here are thought to correlate with an early Cretaceous package in the Barrow Group offshore. And once again, you can see that these major drainages that today drain the Hamersley province, like the Ashburton, Cane, Robe and Fortescue's rivers, basically, similar, or rivers in a similar sort of situation probably fed these early Cretaceous sedimentary sequences. This was also a period of major incision or incision of major paleo valleys. So the diagram on the right here, this dark grey colours here, show the distribution of these major paleo channel features across the West Australian craton, which is this grey area here. The largest of these paleo valleys is the Fortescue Valley here, which still is a valley, very obviously so. It's now infilled with the earliest sediments are these late Cretaceous rocks, locally known as CZD1. They're fluviatile. And also there are then the other two sedimentary sequences that are found across the Hamersley province, the Cenozoic detrital rocks, CZD2 and CZD3. In the Yilgarn, these valleys are not so obvious if you're just driving across the craton, but from the air you can see they're marked by chains of salt lakes. Moving on now to the Eocene, this is a period where we start to see widespread uplift right across the West Australian craton. This is actually driven by regional scale plate reorganisation. This is the time that India actually collides with Eurasia, basically, and there's a major plate reorganisation. The rift zone between India and Australia terminates, basically, and they become part of the same plate. This is seen as the response is seen as a broad uplift across the West Australian craton, and it's at this point that there is incision of inset valleys into those broad, open Mesozoic valleys across the Yilgarn block. In the Hamersley province itself, they're superimposed on top of this sort of broad wavelength uplift. There is actually a discrete domal feature, probably, this is uplift, probably in response to it's called dynamic topography, in response to mantle upwelling. It's clearly visible in today's topographic map, so I've coloured the contours here with high, the mountains are coloured in warm colours and the coastline in cool colours, basically. So you can clearly see that there is this domal region which coincides pretty much exactly with the distribution of the Hamersley Group formation. This is what we've called the Hamersley Dome, basically. So it's a topographic dome, presently, it's still visible today. And it's also, it's the reason why the highest mountain in WA, Mount Meharry, is actually located in this ancient cratonic part of the state. And this is the period at which there was major incision of those CID channels from their sort of early meandering form, which was a response to a fairly flattish terrain. All of a sudden there was this domal uplift, and those channels were incised. Finally, just looking at the actual on-the-ground evidence, what is the landform evidence for uplift? Well, anyone who's sort of stood on a high point in the Hamersley province and looked out across the province will notice that you see a smooth undulating land surface, which is clearly a paleo land surface, which is being currently cut back into by more recent erosional processes. And this concept of an older land surface was first put forward by Campana in 1964, so it's quite an old concept. There are a variety of landforms that are indicative of uplift. So the drainage patterns of those three sedimentary sequences that are found across the Hamersley province, the CZD1, D2 and D3, their drainage patterns are pretty much coincident, which indicates that the drainage systems didn't change very much over about 100 million years from the late Cretaceous to the present. And that's actually quite, that's a signature of long wavelength uplift, basically. Topographic inversion, well, there are beautiful examples of these fluviatile piezolytic units. This is the Robe River area. So these fluviatile piezolitic units now outcrop as mesas. So they've been cemented as a lateritic jury crust. So they're nice hard resistant surfaces at the top, but they now outcrop as a series of mesas, and the modern stream system actually follows along the flanks of these mesas. And finally, many of you will have been to the Karijini Gorges, and if you stand, for example, on the edge of Dales Gorge here, you can clearly see that the gorges have been incised into a pre-existing peneplain. So there are plenty of landform examples that are telling you there's been recent uplift in this area. Summing up the geodynamic history, this is a little cartoon. So elevation is on the y-axis and time is on the x-axis from 300 million years ago to the present day, basically. It's highly schematic, but basically the red line here is what's happening to that ancient Precambrian surface over time, and this dashed line here is actually the modern land surface, allowing for some erosion. But what this illustrates is the history I've just gone through. At the end of the Permian glaciation, we had burial of the craton, re-exhumation through the Jurassic. The craton was re-exhumed by the early Cretaceous, and there was gradual uplift, but then a very sort of pronounced period of uplift from about 50 million years ago in response to that plate tectonic reorganization and the dynamic topographic response to mantle circulation beneath the Hamersley province. So that's the geodynamic story. I want to move now on to the paleoclimate history and what we can piece together of that. What I've shown here is some oxygen isotope data. I've sort of bodged together a couple of different graphs from different papers, but basically you can see temperature, hot is to your left, cold to your right. So basically global average temperatures there are three climatic optima that you can see over the last sort of 120 million years. A major one in the Cretaceous. The Cretaceous was one of the hottest and wettest periods of Earth history. Another significant one in the Eocene, and a further one in the Miocene, superimposed on a gradual decline as we head into the ice ages here. This is also supported by palynological evidence from the Hamersley province. So in the mid-Eocene, there are some samples taken from Glen Flory Station, which is to the southwest of the province, that indicate that there were temperate rainforests in the area during the Eocene. So there are Nothofagus spores, etc., in those sediments. By the time we get to the Oligocene and Miocene, things are possibly a bit drier. The climate is strongly seasonal and probably monsoonal. So we've got a slightly different assemblage of plants present in the Oligocene to Miocene. Now, superimposed on top of this global climate oscillation is the fact that Australia moved very rapidly from the Eocene to the present day, from about 55 degrees south to 23 degrees south. So basically it had started to separate from Antarctica and then moved that separation took place very rapidly over that 45 million year period. And Australia's, the Hamersley province now sits at that latitude where around the world you find the major deserts in the world. So, it's a latitude that's known for its particularly dry conditions. And on top of that, of course, the global climate is also cooling. At this scale, you can't see the anthropogenic warming, but the global climate itself is cooling, and with cooler climates, they tend to be drier as well. So there are two factors at play there, both pushing towards a trend to aridity over the last 20 million years or so for the Hamersley province. What evidence can we see in the sedimentary record? I've done a very brief cartoon here, highly schematic. So we basically see the bedrock, so the banded iron formations, for example, and then three distinctly different packages of sedimentary, we generally call them detritus in the iron industry, three different packages. The oldest, which although they were thought to be Cenozoic, in fact they are late Cretaceous in age, an Oligocene Miocene package and a Pliocene to Quaternary package. And there are three distinct jury crusts developed, indicating multiple episodes of lateritic weathering in the province. So at least two periods of warm, wet climate. We can say that confidently because we can find these lignitic and siderite-rich clays preserved at the base of both the CZD1 and CZD2, illustrated by this chocolate brown here. At least 3 periods of lateritic weathering, as I've indicated here. So there was weathering of the bedrock prior to the late Cretaceous sedimentation, and again that was Jura-crusted prior to the Oligocene, and there's Jura crust formed on top of the CZD2 deposits, and then of course there's modern day weathering on top of all that. It's still carrying on today to some extent. And finally, we can also see evidence that the climate's starting to dry out. So towards the top of this package here, we start to find carbonate deposits and calcretes developed, for example, the Oakover Formation. And when you go to the Yilgarn, you can see that there are player lakes developing. So we've got sedimentary evidence of this trend to aridity over the last 20 million years. Regolith dating, there's been a lot of this work done over the last 20 years or so. And again, this comes up with a fairly consistent story of 2 major periods of lateritic weathering. I need to point out that what we're dating is basically the end of a period of lateritic weathering. It's once the climate starts to dry out a bit and the ferruginous Jura crust gets sort of cemented and fixed in place. Iron and manganese become immobile once again. So what we're dating here is actually the end of that lateritic weathering period. So we know that there was one major period that occurred in the late Cretaceous, so prior to about 65 million years. In the Pilbara, we've got uranium, thorium, helium dates that indicate that there are detrital fragments and piezolytic cores in the CID that are of this age. And across the Yilgarn, well, in the Yilgarn, mainly the north and east, we're also seeing some of these very old ages. And multiple different sort of approaches to dating reveal this dichotomy. So we've got paleomagnetic ages, kaolinite from weathering profiles, and allanite as well. Then there was another major period in the Oligocene to Miocene. And some of that is still going on today. So the older ages are preserved in the Yilgarn and the Pilbara region. And the youngest ages from the southwest, which of course is the wettest part of the state today. So some of those ages have come back at essentially 0, which means that these regolith minerals are still forming and dissolving at the present day in that wet southwest corner of the state. So basically the trend to aridity has terminated this period of weathering, but it's been diachronous across the craton. And I've tried to summarize that in a little sort of cartoon on the right here. So basically the ages we've got for the Martite-Goethite event, basically Eocene to Oligocene, overlapping probably with the channel incision, and then the CID sediment accumulation is rather later, Oligocene to Miocene in age. There's the Oakover Formation, which is this calcrete, indicating a drying climate towards the end of that period. And then the regolith dates and the dates of the cement in the CID deposits, two lots, so the 60 to 65 million year old dates, and then this broad period sort of post about 35 million years old. Okay, so putting the iron mineralization then into this climatic and geodynamic context. Again, I've got another of these little cartoons. So we've got elevation and temperature on the y-axis, and time from 100 million years ago, so this is a different scale, 100 million years ago to the present day along the x-axis. The solid red line is meant to indicate the climate fluctuations, so three main climatic optima, and this dashed line is basically what the elevation of the Precambrian surface was doing, so gradually rising and then rising quite rapidly as the Hamersley Dome started to form about 45 million years ago. Superimposed on that, we can place the MG ore formation in this period here, and the CID ore formation in this period here, with the underlying channels that host the CID mineralization probably overlapping with the MG ore formation in time. So both the CID and the MG deposits, they're supergene. So two things are critical to them both. One is uplift. So in terms of the MG deposits, you need uplift because this This removes the depleted source material and brings fresh, still iron enriched. In fact, recently iron enriched, presumably, recently ore formed material back into the vadose zone to propagate that system onwards and downwards. In the case of CID deposits, obviously you need erosion to incise those channels and to provide the sedimentary input into them. We also need a climate that must be at least seasonally wet, because of the ore fluids in the case of MG ores are basically modified meteoric water, and in the case of CID deposits, well, they're fluviatile sediments, so you must have had an appreciable amount of rainfall to have rivers that flowed presumably most of the year, rather than today's ephemeral ones. And the other point that I need to stress is that iron is only really mobilized in a reduced state as iron 2+. So you probably need mildly acidic and reducing conditions to actually mobilize all this iron that we're seeing preserved now in the deposits. So putting the martite-goethite deposits into context, they are shown here by this pink bar here. So we had a temperate and seasonally wet climate in the Eocene, abundant vegetation at surface. So you had a source of a way of acidifying your meteoric runoff en masse. And this acidified meteoric water leaches the iron in the vadose zone and brings that iron below the water table into the ore forming zone. Uplift of the Hamersley Dome also commences about this time, and this brings unleached BIF and sometimes previously mineralized BIF into the vadose zone, bringing more iron into that zone to be leached and further propagating the ore fluid plume down dip, down bedding planes. And finally, in a hot, wet climate, you're likely to get karstic dissolution of the Wittnoom Formation. This is the major unit that essentially separates the Barramamba and the Brockman Iron Formations, and forms the valleys between the BIF ridges in the area. This results in locally or mildly alkaline groundwaters, and it was probably the contrast between those alkaline groundwaters and the acidified, iron-rich, meteoric derived ore-forming plume that triggered the mineralizing process. Moving now to the CID deposits. We need to go a bit further back in time here to consider their genesis. So starting in the late Cretaceous and the early Paleocene, this is when the sediment source was essentially prepped. There must have been little topographic relief at the time, so you've got likely to have had a thick laterite profile developed. Again, we're in the Cretaceous still, so a very hot, wet period of Earth history. You're likely to have had a thick laterite profile developed, and your rivers are likely to be meandering because the terrain is flattish. Intense weathering, this obliterates any primary textures in the BIF fragments, the superficial BIF fragments, and dehydration during the Paleocene and formation of the ferruginous Jury crust basically forms that hematitic, that featureless hematitic material that forms the cores of the pisolites. Also, as the climate starts to dry into the Paleocene, this would favour bushfires, and you would get generation of abundant charcoal fragments, and these are a very distinctive feature of the pisolitic CID deposits. They form cores to the pisolites as well. Then moving forward to about 45 million years ago, and that's when the Hamersley Dome starts to poke its nose up. The hematite and charcoal fragments are gradually, they move down slope, they roll down slope. This is the period at which the goethitic cortices develop on those pisolites. So the pisolites have a core, and then these concentric zones of goethite enveloping those cores. So that's the period at which the cortices developed. And also at this period, those meandering rivers become more deeply incised because the Hamersley Dome is rising. Then into the Miocene, this is the period at which those sediments are actually finally accumulating within the channel. The pisolites accumulate, and then they start to become cemented. It's unclear whether the original cement was siderite. It's certainly goethite now. Plateau valleys, so these are the sort of broad open valleys along the northern edge of the province where the Robe and the Marillana formations are developed. they appear to favour CID. You get sediments of the same age as this around Mining Area C, for example, but they're not piezolytic. So there's something about those plateau valleys, those open valleys, that favours the formation of this very distinctive type of sediment, the CID, the piezolytic sediment. And it's possible that the plateau valleys don't have any carbonate around outcropping. They're underlain by the Wheelie Wally Formation, and so possibly the groundwaters locally remain more acidic, and that favours the formation of these CID deposits. Australia then, from about sort of 20 million years ago, Australia enters the mid-latitudes, aridity sets in, and there's also continued uplift going on, because you can see this topographic inversion of those CID, those original fluviatile sediments are now present as mesas. This is the period at which the calcretes form, the Yokova Formation, and it's also the period at which goethitic cementation takes place at increasingly greater depths as the water table drops. Right, so finally, I've reviewed the climate and the geodynamics and tried to set the mineralization styles in context. So why is the Hamersley Province so astoundingly endowed in iron mineralization of the MG and CID styles? I think it's the coincidence in space and time of three major factors. The first of these is having an iron-rich protolith. So for the MG deposits, there's extensive outcrop of BIF. The Hamersley Province is probably there's more BIF outcropping in the Hamersley Province than probably anywhere else in the world. And the map on the right there shows the distribution of in blue, Brockman Iron Formation outcrop, and in yellow, Maramamba outcrop. In terms of the CID deposits, well, the iron-rich protolith was basically this thick, ferruginous jury crust that was produced by the late Cretaceous lateritic weathering event. The second feature that's important is regional scale uplift. In this case, it's the Hamersley Dome. So for MG deposits, it promotes erosion, drives lowering of the water table, and basically replenishes iron in that source region, and promulgates the further propagation of the ore plume, ore fluid plume. In the case of CID deposits, the uplift drives channel incision and aggradation, or infill, that is. And the third factor is, of course, a warm and seasonally wet climate. So this it supports extensive vegetation cover and promotes the acidification of the groundwaters, and it results in enhanced iron mobility for both deposit styles. And the photograph on the right is a lovely view across the Hamersley, across the Fortescue Valley from Marillana. You can see it's overwhelmingly red and ferruginous. And I just want to end with this photograph from one of my favourite parts of the world, the overland track in Tasmania. You think, well, why am I ending with this? Well, here we have Nothofagus southern beaches on the hillsides. These are a temperate rainforest species. We've got buttongrass plains, peaty, boggy, lots of little lakes, ideal environment for mobilising iron. I just want to leave you with the thought, maybe this is what the Hamersley Province looked like in the Eocene. Thank you very much.